Okay, so you've gotten two overview talks, and I'm going to get down into some more details about how we have used tools like OpenLane and the Skywater PDK to produce something that is called Caravel, and it is what you will be using to create a chip to submit to eFabless and get fabricated. Now, the name Caravel refers to a old style sailing ship, and it is one that carries cargo around the world. So I'll let you work the metaphor out yourself. But yeah, we are the chip that we have made is the ship, and your project is the cargo. So once upon a time, back in the 1980s, there was this organization called Moses, which was probably the first of the aggregators that collect designs and put them into a MPW or multi-project wafer run on an assortment of foundries. They did have something similar in idea to the Caravel chip, which is that they would provide a template for an area of a chip. In this case, this I'm showing here, one that was a 28 pin. They also had a 40 pin design. And as long as you made your design, you would use pads that they provided and generate a chip in this particular aspect ratio and size. And as long as you followed those rules, then they would take care of all the wire bonding and put it into the technology of the day, which was a ceramic dip package. Here it's a 28 pin dip, and mail it back to you, and you would get a chip with your design on it. And that worked very well. They had essentially what was sort of an open PDK. I will explain the limitations thereof in a bit, but it was enough of an open PDK that you could publish your design and show certain aspects of it in papers that you write and so forth. So here's a design that I made back in 1997. And it was based on the Moses Tiny Chip 40 pin design and showing the longevity of open PDKs. A couple of years ago for a talk, I brought up that design from a disk that I had, and I can still read it, I could still manufacture it, although the process I did this on no longer exists, and I would have to update the design itself for a different process. But the data is all there and is essentially unchanged. So fast forward now to 2022. So what do we have that's different from what Moses was providing back in the 80s and 90s? Well, we have got the Google Skywater Open PDK, and that makes a big difference. We also have all sorts of community-based infrastructure, such as GitHub. And GitHub is where people put code, and as it has been very good for people putting software projects, it is also very useful for people putting hardware projects. So we have been using GitHub as the basis for having users put their designs somewhere that they could be publicly accessible. And while it's publicly accessible by anyone, it's also publicly accessible by us to download it and pull it into our MPW runs that we do on Skywater. So the public forum has changed its official name. It's still available from this location. As Mohamed said, we are expanding to include global foundries and other processes. So we are trying to get away from being tied directly to the Skywater name, but you can still get there from here. This is the metal stack of the process that you will be designing to on Skywater 130. It's got 5 metal layers and a local interconnect of titanium nitride, which is sort of a poor quality metal at the bottom. It is 130 nanometers. In practice, the minimum transistor length is 150 nanometers for obscure purposes, obscure reasons. But that, generally speaking, 6 layers of metal interconnect is plenty to route complex designs like microprocessors. So this is what we have to draw on to create the design that we wanted to make for for users to use. And that includes a whole bunch of design IP. Right now, we have ability to pull open IP for RISC-V microcontrollers, the open description of the Wishbone bus and the various cell libraries that we get from Skywater, also community-generated cell libraries. We have the community itself to provide expertise, and we have all these tools such as OpenLane and others to do all the automation. By comparison, when Moses was doing it, we had a few cell libraries for the I/O. We had a few open tools for doing layout, and that was essentially it. So this greatly expands the range of what can be done. And there you go, allow us to make open source chips. So here's the Caravel architecture. This is what we're providing for the user projects to use. We've got a RISC-V processor at the center of it. Everything here, the white and the pink blocks, is what is put into a single unit, which is the SoC, system on chip, that goes at the bottom, and you can make use of that system on chip to control things. Now, thinking back to that chip design that I had in the Moses process, that had no digital on it whatsoever. It was a mixed signal system, but digital would have to be brought in through pins, and all testing would have to be done by individually controlling signals from a board. No processor, because I didn't have the synthesis tools back then. Verilog was practically new back then. Hardly anybody knew it. It wasn't taught in universities. And so I didn't have that infrastructure. That infrastructure is exactly what I could have well made use of at the time. And that's what we're providing to you to make testing of your project, whatever it is, to be a lot easier. So not only do we have the processor for which you can write programs, but to communicate with the outside world, we have general purpose IO. That means digital IO, input or output, bidirectional. We have what we call a logic analyzer, which I'll get to in a little bit of detail in a minute, which is how you can, more ways you can talk in digital signaling to your user project. For creating programs for test, we have things like counter timers, interrupts, resets, clocks. For communicating with the outside world, not only do we have the GPIO, but you can configure an SPI master, and UART for talking over a serial line. And of course, the processor has RAM associated with it, and other things. I'll get into these blocks in a little bit of detail in just a minute. Mohamed Shalan showed a picture, very small, of this chip here, which was our prototype for this design. This doesn't include the user area, but it's just our infrastructure. It has, at the time, it had a PICO-RV for the RISC-V core, which we swapped out for VexRISC. But these are all the things that we were able to pull together to use, which is an IO pad frame from Skywater IP, the PICO-RV32, which was a open, publicly accessible core for the RISC-V processor. We had the Skywater standard cell libraries to use. We were able to get a pre-built SRAM block made for us from the OpenRAM project, which is also open source, and build it with the open EDA tools we had. So that was probably the first of the purely open source chips. Every single thing in this chip was open sourced. And so that finally leads to our final design. This is an early version of it, but it's essentially the same thing, which we call the harness chip. So whether you want to call it the Caravel cargo ship or a harness, it's the same principle. We provide the infrastructure, you put the user project in it. And it's essentially the same thing that I showed on the previous page, except for having this big user area at the top. And that is where you will create your user project that gets dropped into that area, and that becomes the chip that's manufactured. You can then make use of all the infrastructure here to communicate with your project, or your project can communicate with the outside world directly. And that's essentially your choice. The user project harness, this chip itself is 3.6 millimeters by 5.2 millimeters, and all this infrastructure is fixed. So we give you a fixed pad frame, and the fact that all this stuff is fixed and not configurable by you makes it easier and cheaper for us to make this whole thing available, because we can reuse this every single time. I think I've covered most of these blocks, so I'll continue on. The user project area itself is just a little bit over 10 millimeters squared, which is a pretty good area for doing anything up to the size of a small microprocessor, with a fair amount of RAM involved. Like this is the area for about 2K of SRAM, so you can sort of estimate how much SRAM you could end up putting into a user project area. You have available to you up to 38 general purpose IOs to communicate with the outside world, and various other signaling, but that's essentially the pad frame for the Caravel chip. We are, like Moses, an aggregator of projects. So whenever we do an MPW run, we're going to send 40 projects to that run. This shows a reticle. A reticle is what goes into the machinery. You create a mask that is one reticle size, and that's stepped over the size of the wafer. And on it, we have 40 projects in a 6x7 array that leaves 2 extras that are left over for Skywater to put their own test structures that they can use to characterize the process with. On top of that chip, the modern way of doing packaging is called WLCSP. That's wafer level chip scale packaging, otherwise known as bump bonding. So where we have a regular looking pad frame around the edge of the chip that translates to a bunch of wiring on top in what's called redistribution metal layer on top, and what you get is a flip chip package, which has solder bumps in a 6x10 array, and that is fabricated directly on top of the chip. It's in quantity, it is the cheapest way to do packaging, as the chip itself is the package, and you just, as they call it, flip chip, you turn the chip upside down and put it directly on the printed circuit board and run a wave flow soldering on it to adhere. So in addition to those 38 IO that you can talk to the outside world with through the board on which it is attached through the bump bonding, there are additional digital signals that you can talk to through the IO. We call this the, quote, logic analyzer. The logic analyzer is a fancy name for just basic digital input output. So it's essentially, you've got a wishbone interface on the processor that's memory mapped to a memory address in the address space of the processor. And that allows you to set data inputs to your user project up to 128, simultaneously pick 128 outputs going back to the microcontroller. So you don't have to be limited to 38 signals because that's what's on the pin. Just bear in mind that the logic analyzer doesn't give you immediate updates like you can get if you are communicating directly to the outside through a chip. You'll have to pull from the microcontroller or use an interrupt. The best use of these is to have some kind of configuration setting, set it once and let it go. But you can do some real-time monitoring with this as well. The GPIOs are set up in such a way that they can be used by the processor or they can be used by the user project, and you can switch between them by having a program running on the processor that sets up each GPIO to do what you want, either management use or user project use. The pads are ridiculously complicated. They have lots and lots of modes. We have tried to simplify that by reducing the user view of the pads to essentially 3 signals: input, output, and output enable. That allows you to do basic digital output, digital input, or bidirectional. All these other things will set threshold voltages, CMOS, TTL, compatibility modes, and most of it you just want to set and forget. Will provide settings that you can put in the C code, that you can refer to the configuration of the GPIO by a name like user output or management input or whatever, and that makes the programming of this relatively simple, and you don't have to worry too much about what all these bizarre modes are for. There are some additional functions available on the processor besides the processor itself. There are interrupts. So if you want to do more precise timing, you can have your project interrupt the microcontroller and have an interrupt routine running on the microcontroller to process that. Likewise, if you want to do some precise timing, we've got counter timers available as IP connected to the SoC. The wishbone interface between the microcontroller goes directly to the user project. So you always have the option of writing a wishbone bus slave on the user project side. For instance, I had a project recently I had way more than 128 digital connections that I wanted to go to the SoC. So what I did was I just essentially recreated the logic analyzer within my project, made it 200 bits, and had all the programming I needed to do. So I was bypassing the logic analyzer and creating it myself through Wishbone. That's the way to go. There's also like an additional independent clock that goes to the user project. And then there's also this extra module that will do pass-through programming of the SPI flash straight through the pins of the Caravel chip. We have power supply monitoring. That's not especially useful in the board as we give it to you, because the board as we give it to you just powers up and powers up the user projects immediately. So power monitoring is not especially useful for that. There are a few other things, like we've got a digital locked loop. You can use that to up the speed of the clock from the 10 megahertz clock that we give you on the board up to, say, 40 megahertz, which is the limit of the processor. Although with the independent clock going into the user, you can potentially get as much as 150 megahertz. So as far as building the user project, when you run OpenLane, we have scripts to do that. They will build out not only the synthesized part of your circuit, but then wrap that in the proper power grid and make sure that the connections go out as they are supposed to connect to all the pins in the wrapper. Starting it is a simple matter of cloning the repository. We have a repository called Caravel user project at this address, and all you need to do is a git clone on that and follow the instructions. There are pointers to sets of instructions from that project that you can reach. Essentially, all you do is you take your own Verilog source and you replace the example Verilog source in that project, follow the instructions. It will go through synthesis, place, route, assembly, and verification, and give you a user project user project wrapper completed layout that can be submitted to eFabless. We give you a development board. It looks essentially like this. You got your user project on a chip that's on a daughter board, and we have a serial to USB interface, a USB connector. All you need is this board, a USB cable. You plug it into your laptop. You plug the other end to the USB. The USB 5-volt power powers up the project, and you're ready to go. The power up sequence, there should be a C program that you have running on the flash SPI, the SPI flash that's on the board, and that does the following things, which it configures the GPIO, it resets your user project, and it can control and monitor the user project. This just, sorry, I'm running out of time. So this just reiterates the fact that the GPIO pins are controlled either by the user project or the microcontroller per the way you want to control it through the program. There are three basic forms of validation. Validation through simulation, which will use iVerilog, or there's a freeware program called CVC that will do simulation with parasitic annotated timing, and a physical validation, which means DRC and LVS. That's all taken care of automatically. as part of the synthesis tools. This is just a verification to make sure that the synthesis tools did their job. And then there is the pre-check process, which does all these final checks and makes sure that the DRC is correct, layer density checks, XOR to make sure that your project is in fact exactly where it is supposed to be, with the pins on the wrapper matching where they're supposed to go on the harness container. So for submitting the project, you register with eFabless and we'll follow the instructions there for how to submit to an MPW run. You can create your project either on or off the eFabless platform. And assuming that you're doing it off platform, when you create your project, it will get populated from your own Git repository that you've made public. You submit your request to manufacture through a form on our website, and then we will automatically take your user project, assemble it with the Caravel harness chip, run it through all the pre-checks, and you get a pass-fail pre-check report. After that, it goes into manufacture, and after some time, you get back the chip assembled on a development board. The development board no longer looks quite like this. I didn't have time to update the slides with a picture of the actual board, but it's about half this size. And it has the USB, and all, as I said before, all you need to do is have a USB cable and you can plug it into a laptop. We have Python scripts available for programming the SPI flash or talking to the chip through serial. And if you have done your proper simulation validation, then you have hex files that you can program directly into the SPI flash and be running exactly as you have done the simulation in minutes from getting that board. There are example projects to be found on our eFabless website. This is just a very, very small list that came from the first 1 or 2 MPW runs. There are now hundreds of designs up there, and feel free to look through them for inspiration or examples or finding things that you might need. And of course, the community is available too. So that's pretty much what I have to say about the Caravel harness chip. And I guess now you go to the demonstration part of this workshop where you'll get to put all this together and see it in action. So thank you very much.